So as I said at the beginning, we deal with surfaces that are in difficult environments, that respond to these difficult environments or function in these difficult environments. So they include reactive fluids, high temperatures, stresses, we said, right? So because of these harsh environments, it has been traditionally challenging to reach to these interfaces and see how they behave, okay? And we have developed new experimental capabilities in our laboratory to be able to visualize these materials at nanometer or even atomic scales, but in those representative difficult environments, so temperature and reactive gases. And the specialized instrument that we have is called scanning tunneling microscopy that functions in situ at high temperatures up to 600 degrees C and in reactive gases of oxygen, water vapor and hydrogen. And it is this capability that actually allowed us to see the different behavior of the pyrite surface compared to the bulk that makes us now know that the reaction kinetics on those surfaces should be treated differently compared to how the bulk behaves. So with this new experimental capability in our group, we can quantify the electron transfer properties under these in situ conditions and visualize the correlation of these electron transfer properties to structural differences on the surface, okay? But we cannot quantify the chemistry, the elemental nature of the surface with this technique. Therefore, now we are in the process of developing new capabilities and use new capabilities from other facilities, such as national synchrotron facilities, to also quantify the chemical nature of the surfaces, not only electronic and atomic, but correlate those to what are the compositions and chemical environments that evolve on the surface. So then let's go back to the example of fuel cells, okay? And these are also complex oxides. And again, their surfaces differ from the bulk, not only electronically, but we suspect also chemically, compositionally. So you take a compound, let's say lanthanum manganite, so it has three different types of elements in its bulk, and there is a certain stoichiometry to the bulk. But when you come to the surface, we realize that that bulk composition no longer holds. It can drastically differ in terms of its composition and phase structure. And it's that interface, the very surface, is what reacts with the environment. So in a fuel cell, we want these reactions to be very fast. And if you do not know what is exactly on the surface, then you cannot define the relation of structure, chemistry to the property, to the reaction rate that we are trying to accelerate. So we really want to see what exactly, which atoms are on the very surface that are inducing the reactions or that are blocking the reactions, so that we can design our materials to make use of the better ones that go to the surface and to try to eliminate the ones that suppress the reactions on the surface.